so we are in the second lecture on logistic regression. Now, what I want to do today is to quickly go over what we have discussed last time and try to connect logistic regression to our favorite deep neural network models that you see nowadays. So I want to draw some connections there. And then I also want to draw some connections with Bayesian decision rule so that we can now try to link all the methods so far we have learned. So far we have learned Bayesian decision rule, we have learned the linear regression, and then we are now learning logistic regression. We have seen some connections between logistic regression and linear regression, so we want to also bring some connection to Bayesian decision rule. I want to make you understand that all these classifiers, there are some underlying common principles. If you try to go online and watch a video, you learn method A, B, C, D, E, F, G, X, Y, Z, and you feel that they are all completely independent. That's not what's going on. All these methods, there are some similarities. Under certain conditions, they're actually doing the same thing. You need to understand the subtle difference between all these methods. All right? So here's my job to really make that point clear. And then afterwards, we want to study a few case studies of will logistic regression really buy you something that the linear regression is not going to buy you. So we want to look at those cases. All right. So this is again the same slide that we have gone through for many times. We're talking about discriminative methods, and we are in this branch. We're looking at logistic regression. Very soon we will look at support vector machine and also neural networks. Okay. So the plan for today is to go through these three topics in logistic regression. We have gone through the convexity a little bit last time, so I want to do a quick review on convexity again. Then I want to talk about gradient descent algorithm, because for logistic regression, since it is an optimization-based classifier, it's a discriminative method, we should expect to use some standard optimization tools to find the model parameters. That is gradient descent. We want to derive the gradient, and then we want to look at the gradient descent step, and then we want to see how this can be plugged into this gigantic pipeline that we have spent time on the first part of the course. Then I want to talk about the role of this regularization, and how will the regularization help you get better estimate in this logistic regression setting. Part 2 will be on connection to Bayesian decision rules, and then I want to give you some interpretation of that. And then part 3, I want to compare with linear regression. Okay, so this is a diagram that we saw last time. The meaning of a logistic regression is that you have a data point here and there, and then you want to find a line that can fit all these data points. Now, if you use a linear model, then it would be a straight line. Okay, so that would be the linear regression. It's a straight line passing through all the data points, and we say that by finding a straight line, it's not a very good fit, because the data, they are lying here and there. If you use a straight line, there are lots of data points that they're just not close to your curve. And therefore, logistic regression gives you this curve. It seems that I can fit better. So that's the underlying idea of logistic regression. We want to find a nonlinear function that can fit these data points better. The form of the logistic regression is 1 over 1 plus e to the power minus something, and the something is a linear form. Now, this can be regarded as a soft version of the sine function, and by sine function, I mean that you take a discriminant function, which it gives you some number. Usually that is a linear regression model, so you have a straight line, and then you say that if this number is bigger than 0, I'm going to return you +1, otherwise I'll give you -1. The same thing can be used for the logistic regression. However, you replace the sine function by this, we call it soft decision rule. Okay, so that is the soft decision rule that is going on with the logistic regression. This function is called the sigmoid function. Sometimes people call it the logistic function. Okay, so There is a very close connection between logistic regression and also the deep neural networks. Now, if you remember when we introduced deep neural network, we are thinking that there would be a big component that is trying to extract the features. So I give you an image, and then you go through all these deep layers, and after all these deep layers, you'll be able to pull the features. And the last layer of this deep neural network is usually taking this form, where you have all these feature vectors, x1 through xn, and then there are weights, and w0, w1, w2, w3, and so on. You add them together, and then you put a nonlinear activation function. Does it look familiar to you? Okay. So that is a typical neural network setting. Of course, in deep neural network, you're going to cascade these multiple times to construct a very deep layer, but that is more used to extract the features. When you go to the decision stage, what you're doing is that you have something like this. You have a soft decision rule, which is a sigmoid function, and before that you have all these weights, and then you have all these features. When you look at this diagram, you see that there is a very interesting connection with the logistic regression. What you're getting from here is that this is a linear combination of all the x multiplied by the w's, and then you add w0. That would be the expression, w transpose x plus w0. That is a linear expression. And then after you go through the sigmoid function, essentially just apply the sigmoid to this linear response. And so this sigmoid function is what? Well, the sigmoid function, according to our definition, this is just 1 over 1 plus e to the power minus something. And that is the logistic regression model. Right? So you have spent a lot of time extracting the features, but afterwards, when you go to the decision stage, in many of these deep neural networks, they are running this logistic regression. And therefore, by studying the logistic regression, we can somehow understand a little bit what's going on in the deep neural network. I'm not saying we can understand everything, because you still have a deep part which tries to extract the features. But at least, if you look at the last layer, we can say something about it. We can at least know, this is a linear classifier. It has certain performance. It has certain behavior. That's the connection. So to understand the logistic regression, we introduced this loss function last time. And the loss function is taking this form. It's called the cross entropy loss. Now, in this lecture, I'm still focusing on two classes. So you have binary case, yes or no. The cross entropy loss for a two-class problem is a sum of these two log terms. The first term is yn times log of h. H will be the decision rule. It will give you either +1 or -1. And then the other one will be 1 minus yn, and then you have log of 1 minus h. So we introduced this idea that if your true label and also your prediction they are matched, then your loss will be 0 in this case. Or if they're both they match in the case of both 0, then this will also be a 0 loss. Otherwise, your loss will become minus infinity. When you put a minus here, then your loss will become plus infinity, and therefore you want to find a good edge such that all these loss they will be minimized. Now, of course, the difficulty is that this h is not a binary rule, right? Because h can give you something that has a transient, and so that will give you some room of tuning a theta that can minimize the loss. Otherwise, it will just have either plus infinity or 0. So that is a little bit harder to optimize. If you really insist of putting a 1 and 0 here, then it will go to something called the perceptron algorithm, which we will learn later. There is a convex property of this training loss. The convexity comes from the derivation that the previous slide, you can write the loss function as the following. And then we introduce a concept called the log odd, and we show that this is essentially the same as theta transpose xn. And so the first term in this training loss function is convex. It's linear, and therefore it is convex. then what we are going to do is to look at the second term. We want to show that the second term is also convex, and to do so, we just need to take the gradient twice and look at the Hessian and show that the Hessian is positive semi-definite. And so we went through this exercise last time. It's a little bit tedious. I'm not going to go through it again. I just want to show you that the gradient takes this form. It's very interesting because the input has a h. The gradient is also in the form of h times your input data x. The Hessian matrix of this logistic training loss, you can take the second order derivative, which is taking a derivative on the first order again. Then you can show that the second order derivative takes this form. And note that h is between 0 and 1, and so 1 minus h is also between 0 and 1, and therefore you just need to take care of the last term. But the last term is positive semi-definite by construction. And so you have shown that the training loss function is indeed convex. So here is the derivation showing you why the Hessian is positive semi-definite. Okay, so after you have gone through all these, you have shown that this training loss function is convex in theta, and therefore, as we discussed the last time, you can use a convex optimization algorithm to try to solve this logistic minimization problem, right? So if you map to the pipeline we introduced in the beginning of the course, we know that there will be a model. This is the model. And then there is a loss function. This is the loss function here. And then we say that there should be optimization algorithm. The optimization, in our case, it would be a convex optimization algorithm to solve. But if you have a lot of data where your CVX program doesn't handle, then you can just write your own gradient descent algorithm, which is a little bit more tedious, but it's doable. Okay, and so you have optimization algorithm to solve this problem. By solving this problem, I mean that you find a good theta that can minimize this loss function. Now, if you want to use CVX, as you will be asked to do in the following homeworks, I think it's homework 4, what you want to do is to rewrite this loss function in a syntax that CVX likes, and the syntax will be called the log sum exponential. So you need to write this equation into this log sum exponential form. Then you plug into the CVX program and then click a button, say begin, and then it will return you a solution. Otherwise, again, you need to write your own gradient descent algorithm and get suffered a little bit from your bug. Okay. All right. Now, this is a diagram I generated on my computer. Okay. So we've discussed this last time. Okay, so, okay, I think I made a mistake here. It's not the black, this is red, and then this is, So, you start with a true model, which is the red line. The true model is it tells you the distribution, that how are you going to sample the zeros and ones. And then the blue circles, they are the training samples that you draw from the red line. Then you run this convex optimization, you get a black line, and then you can see that if it does properly, then your black line will be pretty similar to the red line. Okay, so you can do this exercise at home. All right, so this is where we are left from last time. Now, if you have a lot of data points, and then your CVX is not happy, okay? Meaning that you click a button, it takes you more than 2 minutes to get a solution, then you know that the CVX has some memory issues, so you know that the problem may be too big for your program to run. Then you start to need to consider running your own gradient descent algorithm. The good news is that for this logistic training loss, the gradient descent algorithm is actually not too bad to write, because I have a training loss function and I can calculate its gradient in closed form. So the only matter is that I need to choose the right step size. But as usual, you can always make the step size like a trial and error type of thing. Okay, so you start with something big. If it doesn't converge, try something smaller. Okay, so this is the training loss, and then we can calculate the gradient. And so we have shown that the gradient of this part of your loss function is given by h times x. Now, what is the gradient of the first part? The gradient of first part is just x, right? So if you take the gradient of this guy, that will give you what? Yn xn. Okay. If you take the gradient of this guy, then it will give you h times x. So therefore, you have calculated the gradient of j, which is given by this one. Okay, so you have a summation of all the n samples. Then you have this h times x. Okay, h times x, and then minus your yn. Okay, so that would be your loss function. Okay, so this is your loss function. Now, you notice that here I am putting this theta k. This theta k means that because I'm running a gradient descent, it's an iterative algorithm. And therefore, I need to plug in my current estimate of my model parameter. And here is the current model parameter. I plug it in, and then I calculate this up. I make an update from my gradient. Then I make a step forward according to the gradient direction. And then the step size is alpha k. And you need to choose a good alpha k. And then run this algorithm over and over. Then eventually, it should converge to the global minimum because this function itself is a convex function. So there should be, you should be able to find a global minimum. Okay, however, when you try to write this gradient descent algorithm, there will be some issue that you may encounter. This happens especially when this term is getting very, very close to 1. So you look at this loss function. This loss function has a term of log of 1 minus hx. So if for whatever reason hx is close to 1, then you're taking log of 1 minus 1, and that's log of 0, and then log of 0 will go to minus infinity. Then it's not fun to work with this case. Okay, so here's is summarized here. So what if h is really 1? Then you have this log of 0, which is minus infinity. So no matter how you change this expression, you can change into this form or that form or that form, you will always have a similar issue. So if this happens, then if you run the CVX program, meaning that you do have data points, okay? So you do have data points. They are really grouped together in their class. All these data points that group together in their points. And then when you try to draw the logistic function, try to fit them, when they fit the data, it's very close to 1. And so when you put into the CVX program will say, I cannot find a solution because you have this log of 0 or minus infinity that's going on in your fitting problem. So I'm not able to solve a solution. Okay? And then so you ask, how can this be possible? You just showed me that the logistic regression loss function is convex. It has all these nice property. It's convex. It has nice property, but then you have this minus infinity. You have this minus infinity issue. Okay, if the data points they're so well behaved. Okay, when you try to fit them, it fits very well, and it goes to 1. Then in that case, the CVX doesn't work. So what you can do now is to add a term of called regularization. In our case, it would be putting a lambda of theta 2 norm square. Once you put it in, then you will be able to find a curve that is that can connect the two classes without any issue. Okay. Now, then you ask, what if I do not have this term? What happens to this function? This function is convex. However, it's not strictly convex, and so you will be able to find a lot of a global minimum. Okay, so the minimum value is the same. However, you will have a lot of these global minimizers. Okay, so it's not unique. And so by putting a regularization here, you are trying to say that, okay, among all these possible global minimizers, I'm going to pick the one that will have a reasonably small magnitude. And by choosing that one, hopefully my theta will not explode. Right? In the previous case, you see that it becomes not a number because the theta explodes. So you can put a regularization, and you need to choose a lambda. And of course, this lambda is really depend on your choice. You can make it bigger, smaller. If you make it big, then this term will dominate. And so you don't care about this theta term. And then this curve will become smooth because having a big lambda, you do want to have a smaller theta, and so it becomes smoother. Now, if you set a lambda really, really small, then you don't really care about this term. You need to care about the stated term, so you want to fit it as well as possible. In that case, you will get a really, really sharp response. Okay? So you can try doing this exercise at home. Try to write your own CVX program for logistic regression. You can create your own data set like this. This is very easy to create. You allocate a few data points around the 0, allocate a few data points around the 1, and then try to fit this equation into your CVX program. Write a couple lines. CVX is very beautiful because you just need to type minimize that function. Literally type that function, and then subject to whatever constraint. Just type that one and then begin and then end, and then click a button. You will be able to get a solution. That's a lot easier to use than writing your gradient descent. Okay? Writing gradient descent, you don't even know if you have a bug or not. CVX is that easy. Okay? Then you can play around your lambda. You don't need to worry about your gradient descent step size. You just play around this lambda. You can get different curves. Then you get a much better feeling than what I'm talking here. If you go to Stanford website, you can see that they have a exercise on MNIST dataset. So the MNIST dataset is a very small dataset that contains digits from 0 to 9. In this particular homework exercise, they ask the readers to just classify between 0 and 1. So 2 classes, 2 digits, okay, 0 and 1. And because 0 and 1s, they look very, very different, by fitting a logistic regression model, you will be able to do a very, very good classification of these 2 digits. Okay, so the actual principle is the same. Okay, all you need to do is to download this data sets, look at all these 0s and 1s, convert this square image. This is a 28 by 28 image. Okay, 28 pixels by 28 pixels. You turn it into a column vector using a reshape command in Python. You get it into a column vector, and these will be your xn's, and then the yn's will either be 0 or 1, as is labeled. Then you build your own logistic regression model and try to fit all data. And then you will see that the fitting will be done pretty well for this particular exercise. So they have provided MATLAB codes. Okay, so if you're a MATLAB user, you will like it. They provide the MATLAB codes. They don't use CVX. They use their own optimization package. Therefore, you need to know the syntax of their optimization package. So you can try to run this exercise. Otherwise, you can wait a little bit until homework 4. You have another similar type of problems, not on this particular data set, but on something else. So you will also have the opportunity to try to implement your own logistic regression. And we will be using CVX. I'm trying to make your life a little bit easier. Okay? In any case, you are encouraged to try this exercise because before you sit down in front of a computer, before you get your hands dirty, you don't really know what I'm talking about.